Today's Computation and Society Initiative. Our colloquium for today, we're really excited to welcome Jon Kleinberg, and he'll be talking today about fairness and bias in algorithmic decision-making. So Jon is the Tisch University professor of the Department of Computer Science and Information Science at Cornell University, and his research focuses on the interaction of algorithms and networks, the roles they play in large-scale social and information systems, and their broader societal implications. He's also a member of the National Academy of Sciences, the National Academy of Engineering, and the recipient of many prestigious awards, including the MacArthur, Packard, Simons, Sloan, Vanderbush Research Fellowships, and the Harvey Prize, Nevelina Prize, and the ACM Prize in Computing. So we're really excited to have him here and hear what he has to say. I'll keep an eye on the chat throughout the talk, and he said he's welcome and open to questions throughout. So feel free to post something in there if you have a question, and we'll also have a little bit of time at the end in case there's any other questions there. So without further delay, thanks again so much, Jon, for being here to chat with us, and I'll give the floor to you.
Okay, well, thanks very much. Thanks very much for the invitation to come speak here. And let's see, I will share my screen, if you can see that. Great. Okay, well, yeah, so it's a pleasure to get to come speak here virtually. And again, yeah, as Elisa said, if people have questions as I'm going, definitely feel free to ask by whatever channel works best. And I guess Elisa, yeah, feel free to watch the chat. So if you, that's one way to get questions into this. So anyway, yeah. So again, a pleasure to be here, and it's exciting to be sort of talking in this series that as part of this Computation and Society initiative that you have. This sort of interface of areas is certainly something that we're also excited about at Cornell, and a number of us have been thinking about. And so what I want to talk about here was some work that is sort of that brings in perspectives from a number of different areas as we think about these questions of fairness and bias in algorithmic decision making, a topic that's become increasingly sort of active over the past few years, as many of you know. So this will be joint work with my PhD student, Manish Raghavan, and then a set of faculty representing three other different areas: Jens Ludwig, who studies public policy at the University of Chicago, Sendhil Mullainathan, who's a behavioral economist at Chicago, and Cass Sunstein, who's a professor of law at Harvard. And we, in a sense, my own arrival at some of these questions, I think, sort of in part reaches back to my, interest in large socio-technical systems, right? If we think about the 1990s, I think, for me as a computer scientist, one of the big realizations to emerge from the growth of the web and the public embrace of the web, online social media, social networking platforms, was the way in which, systems design in computer science had really taken on both a technical and a social component. And if we thought about these systems purely technically, we'd be perpetually surprised at the way they rebounded against our best efforts at design based on the social and economic feedback effects that were going on. And conversely, if we looked at these big systems and thought of them as a place to observe human social and economic behavior, we'd be surprised by the opposite, which was the ways in which actually a lot of the behavior was being shaped by algorithmic decisions that were being made there. And I think all of that is, even more true now, with sort of an added dimension, right? If we think of the technical and the social as two dimensions, one way to think about this emerging line of work in topics like fairness, like societal decision making, is that there is this kind of third normative axis that we're beginning to discover, right? It's as though moving around in this two-dimensional world, we were sort of missing the fact that just because an actor in the system deeply understands both the technical and the social feedback effects doesn't necessarily mean that they will use that knowledge to produce an outcome that we think of as societally desirable. That, it turns out, is a separate question. And I think for us in computer science, that's one of the issues that we're grappling with. Obviously, there are fields that were highly attuned to this point and have been grappling with it for a long time. And so, with apologies for being late to the conversation, I think, computer scientists are starting to arrive at that also and to think about these things. And that's the sort of in a sense, the basis for this collaboration that we've been engaged in with, with this group of people over the past 5-6 years. So if I think about this kind of move from socio-technical systems to the normative dimension, we can sort of start by thinking about a kind of problem that computer science has gotten very good at solving, which is problems like ranking, recommendation, and content filtering, right? So, this is a screenshot from a Netflix help screen where they explain how, the basis of the Netflix recommender system is to take you, an individual with your complex set of tastes, reduce you to a feature vector, pass that through an algorithm, and ultimately make a prediction, a prediction about what is the probability that you will like this particular movie. And over the past few years, people have been looking at offline domains and have been saying, if algorithms are very good at making predictions about people's behavior, where are instances in what we think of as, the offline world, where something like a prediction is happening, right? Something like this pipeline is being followed, people to features to algorithmic prediction with some probabilistic component. You can make the argument that perhaps hiring looks like this, right? That I take somebody with their past job history, I reduce it to some tabular feature-based form like a resume. That resume gets read by a human hiring committee who then, you want to say, makes a prediction, but here it gets a bit fuzzy, right? What exactly is the human hiring committee doing? They're doing something that takes that data and makes a decision. But in fact, the acute challenge in formalizing exactly what we do when we evaluate a resume is actually part of what animates the sort of topics I'm going to talk about. Obviously, some similar thing when you start at the admissions portal to a college like Cornell or Yale, you take somebody's high school educational experience and everything else that's been going on in their teenage years, you reduce it to some feature-based representation. You again pass that to an admissions committee, which is again making a similarly sort of challenging to define kind of decision. But so all of this says that, screening is an activity that we see in many, many different domains, right? And my colleague, David Robinson, who's a visiting scientist at Cornell, co-founder of this nonprofit called Upturn, talked about how at Upturn, when they would write reports about, the dangers of algorithmic bias, those papers, like many papers you see in this literature, start with what you might call the incantation of societally important areas where this comes up, things like employment, education, credit, criminal justice, right? It's a constellation of sort of high stakes domains where we're making decisions about people. And the question is, what happens when we take the traditional machine learning pipeline and we try deploying it in these settings, right? Mapping an individual to features, passing it through some decision-making entity, whether it be human or algorithmic, making a probabilistic prediction. Now, right, there's this interesting point about the word high stakes, right? So I say that these are high stakes areas because, unlike the case of Netflix recommendations, where in the end, it did not matter that much whether it was right that I was going to like this movie or not, right? That's not a decision that's particularly important to anyone. It matters a lot to a particular person whether they get hired, whether they get this job, whether they get admitted to college, whether they get this loan, certainly whether at a pretrial detention hearing, whether they're going to await trial in jail or in the community. Now, so that's the sense in which we're in this realm where individual mistakes are individually costly to people. I should say, it's partly a statement about granularity, this distinction between the low stakes questions of the online world and the high stakes questions here, because I take, decisions about, which news articles to show you, which posts from your friends to share, how to rank search results. Any single one of those might be low stakes, but I take 100 billion of those, and that adds up to something extremely high stakes, like the formation of public opinion in a country as it approaches an election, for example, right? So this is not so much to compare the aggregate stakes in any of these domains, all of which are incredibly high and all of which are important topics to think about, but more just that individual mistakes here are costly. And because of that, I think there's this question that people have been focusing on, the risk of bias for both human and algorithmic decisions. Right. And so I think before we talk about ways in which bias can come into algorithmic decisions, it clearly is useful to talk for a couple minutes about what we know about bias in human decisions. So obviously not a topic one can do justice to briefly, but let me just point out a few stylized observations that are going to be useful in what follows. So this is a topic that has a long history of research in the behavioral sciences, and in some sense gaining momentum through the 1980s and 1990s was this realization that we could see disparities in people's judgments in empirical data, even in cases where the decision maker arguably was not explicitly trying to engage in bias, right? That there was this implicit bias in their decision making. And just to give you an example of what some of this empirical work looked like in the 1990s, here's one classic study that was by two European social scientists, Christine Venevas and Agnes Vold, published in Nature in 1997. What they were looking at was reviews of European Research Commission grant proposals. And think of this as a template for the kind of study that many people did around this time. So they got the reviews of many different grant proposals. And one of the questions that reviewers had to answer was to assign a competence score, as it was called, to the principal investigator. How competent is this person to carry out the research? And so what they did was they took these principal investigators and they tried to find external measures of their impact up to the moment they submitted the proposal. Sort of as many different measures as they could think of. So, number of papers in high-profile venues, number of citations of those papers, past funded grants, success in those funded grants, and so forth. Right, numerical measures, and they put that on the x-axis, total impact. And then on the y-axis, for people who were in different bins on total impact, they looked at the distribution of competence scores. And they found this disparity, which we see in many similar empirical studies, that for a fixed, numerical measure of total impact, you see this gap where men have systematically higher competence scores than women as principal investigators. Or if you want to read the plot horizontally, in order to achieve a similar competence score as a woman as PI, you would need to have a much higher numerical measures of impact. All of these studies, of course, come down to how well can I measure similarity among individuals, which in a sense sort of formed the basis for this influential paper by Dwork et al. In 2012, Fairness Through Awareness, which touched off a lot of this thinking in the computer science literature. The idea that we should find metrics along which people are similar and then ask whether they're also being given similar evaluations. Okay, so this is sort of one glimpse into the kinds of biases that we see empirically and in human decision making. And it's important to say these are aggregate statements, right? We see that there's some sort of disparate evaluation being done. It's very hard to attribute it to any one person or any one part of their decision, and that's often the challenge in evaluating claims of bias, the attribution problem, right? We see a gap, it's genuinely there. If we want to remediate it, we want to know, where is it happening? I'll come back to that point. But first, let me think about algorithmic bias, right? So we have a picture like this. And then we say algorithms, in contrast, have no direct incentive to exhibit bias. I mean, at some level, we all know that. The algorithm is being fed a vector of numbers. It doesn't actually know what these numbers mean. It doesn't know that a particular dimension in those, in that vector, has any particular semantics to it. It's just trying to produce a rule that's going to minimize some loss function. Despite this, there are many sources of potential bias in algorithms. And if you've looked at this topic, you sort of are familiar with some of the basic contours of this. One, for example, is in the features that I choose to give the algorithm, right? So for example, if I were training an algorithm to evaluate, European Research Commission grant proposals, as on the plot on the previous slide, I might say, let me try to keep humans out of it. I'm just going to give it the administrative data from 20 years of past evaluations, and we're going to train on that. But unfortunately, that 20 years of administrative data contains the competence scores that were assigned by researchers. And we've just determined that there's this systematic disparity in those competence scores, right? So if I start feeding in even what seems like sort of just tabular administrative data, it's going to contain the traces of the human bias that's preceded it. I can basically very easily teach the algorithm to reproduce the decisions I was already making, and then it's sort of back to where we were before. So if we wanted to look at an algorithm and say, has it in fact been contaminated by bias from earlier parts of the decision, there's a sort of auditing question going on, much in the same way we have an attribution problem with human decision-making and bias, right? In both cases, we're saying, we see a gap, where did that gap come from? And so that argues that there's a sort of fundamental connection between bias on the one hand and what people call interpretability, right? This idea of, looking at a very complex decision-making process, say like an algorithm, and trying to figure out how it's making the decisions it's making, given the complexity of the algorithm. In some sense, the starting point for the work that Jens, Sendhil, Cass, and I did with this was that is to sort of appreciate that we think about the interpretability problem for algorithms, and there's a lot of interesting work there, but there's a corresponding interpretability problem for humans, that we also don't really know why humans make the decisions that they do. And in fact, implicitly, discrimination law, is oriented around this challenge of interpretability for humans, even though it's often not explicitly phrased as such. We see this, for example, in the fact that, and I'll talk about US discrimination law here in a very high level terms, that the law recognizes, in different forms, two categories of discrimination, right? Disparate treatment, which means that the decision maker, and imagine, let's talk about hiring, for example, is deliberately favoring job applicants on grounds like race, gender, national origin, religion, or age. And disparate impact, which says that regardless of your intent, if a screening decision has a disproportionate adverse effect on a protected group, then at that point, the burden of proof shifts to the decision maker, who must establish the business necessity of the decision that led to this disproportionate impact, right? So business necessity might mean, if I am hiring people for a job where employees are constantly, a crucial part of the job is to reach things that are extremely high off the ground, and I put in a height requirement, then, I may be able to justify that height requirement on business necessity for this particular job as a prerequisite, despite the disproportionate effect it might have based on gender, for example. Conversely, if I'm hiring software engineers and I have a height requirement, that would seem to be very hard to defend on the grounds of business necessity, right? So it's a shifting of the burden of proof. Now, the challenge here, of course, is that it can be very hard to tell if a decision maker has engaged in either disparate treatment or disparate impact. One reason is they might lie. They might lie about the reason they're making their decisions. But a deeper and, in a sense, equally or more challenging reason is that they might genuinely not know their rationale, right? Someone who's genuinely interested in eliminating implicit biases from their decision making might be happy to, completely earnestly talk to you about how they are going about making their decisions. But it could be that they might genuinely just not know the rationale that they're actually using. And this is something that, on the one hand is sort of partly intuitive. If you think about any time you've engaged in say, recruiting in any form, and you have two applicants and you just sort of like one better, it's sort of hard to say from first principles why you made that decision. But it also has a foundation in a long history now of very creative experiments in the behavioral sciences, in which we ask people to make a decision. We bring in group A into the lab, ask them to make a decision. We then subtly change something in the environment, and we bring in group B. The decision changes, but when we interview people from group A and group B and ask, why do you make your decision? No one mentions the one thing that we know we changed in the environment, right? So we can get people to change their decision. They don't actually know why they changed their decision, right? And so here's an example, because it's useful to make this concrete. So one of many experiments that date back to the sort of early work on this by Nisbet and Wilson in the 1970s. They brought people into the lab and asked them to engage in a word memorization task. Okay, so memorize a sequence of words, recite them back. At the end of that, they then asked them this non sequitur question out of left field, which was, name a brand of laundry detergent. Okay, so they think of something. Okay, group B, we bring into the lab, different set of people. We asked them to memorize words, and those words are beach, ocean, moon, waves. Then we asked them to name a brand of laundry detergent. Many more people in group B say Tide, a brand of laundry detergent, because they've been primed by all of those words, right? So this is a priming effect that's well understood. If I say a bunch of words that are all kind of nearest neighbors of something, I can get you to come up with the word that I would like you to, in this case, Tide. But Nisbet and Wilson did something extra, something very interesting, which is they simply asked people afterwards, why did you choose the brand of laundry detergent you chose? And in both groups A and B, people said it's because it's the one we use at home. It's the one my family used when I was growing up. I recognize the, the logo or the brand, I see it at the store. People didn't say in group B, it's because you primed me with all these words. And yet, because of the statistical disparity, we know that in aggregate, many people in group B at some level said tied because they were primed, right? Because you had a much larger effect in group B. So what this and many, many other experiments tell us, right? There are lots of these experiments. Nisbet and Wilson also stood out in front of a clothing store with a rack of clothes, asked people to choose one. And by orienting, it's sort of known that if you sort of orient the rack of clothes, you can almost sort of force the rightmost one onto people, right? So many people choose the rightmost one, but they never talk about position as the reason why they chose it. They talk about color and style and so forth. So this idea of like telling more than we can know, right? The argument that they made, in which a long line of research has reproduced, is that people are happy to give you the illusion of an explanation, right? If you ask people why they did something, people, unlike algorithms, come with this user interface in which they say, here is my rationale. And sometimes, sure, that is the right rationale. That is, to the extent we can make this point even precise, that may be the genuine reason, but it might also not be the genuine reason. And so it's a point, I think, from the behavioral sciences that's interesting for those of us in computer science, because it turns the usual debate about interpretability slightly on its head. It says, yes, there's an interpretability problem with algorithms, but there's also an interpretability problem with humans. It's a different one. It isn't the same interpretability problem, but it's equally profound. And maybe there's something to be gained in the sort of arbitrage between the ways in which these two interpretability problems are different. So this is something that Jens, Sendhil, Cass, and I thought about, that the fact that the interpretability problem for these two kinds of entities, humans and algorithms, are different, means that we get a particular kind of opportunity out of algorithmic decision-making, namely that well-regulated algorithms in which I have access to the machine learning pipeline that built it, I have access to the training data, to the objective function, and I can probe it. They may be able to make discrimination easier to detect. So two things here I should talk about: well-regulated and algorithms. So by well-regulated, I mean what I just said, that I have access to the machine learning pipeline, right? Think of, for example, something like the Netflix prize competition from 10 years ago, where Netflix effectively made available large parts of that pipeline. And we could therefore do a lot of experimentation as we try to sort of decompose the algorithm and then try building it back up. I should also say, just briefly, just so we kind of make sure we're on the same page with the word algorithms, that of course in all of these applications there are really two algorithms, right? There's the training algorithm, which takes training data and outputs a classifier, and then there's the classifier itself, which takes instances like job applicants and outputs either a yes/no evaluation, a probability estimate, something like that, right? Okay, so what do I mean by make discrimination easier to detect? Obviously, we can't read the code and expect to understand the algorithm. There are all sorts of reasons for that. But we can do a bunch of things that we cannot do with human beings in similar situations. We can, for example, look at the set of features that the algorithm used. We can look at the objective function, right? Algorithms ultimately in these settings are optimizing some kind of objective function. And so we're able to have a very specific debate about whether the people using this algorithm for decision making chose a reasonable objective function in a way that we, again, I would argue, can't realistically do with human beings. We can't realistically sit down with a hiring committee and ask, are you using the right objective function? Because fundamentally, the objective function that people are using is not elicitable in any reasonable way. Similarly, we can run counterfactuals with algorithms in a way that we can't run with humans, right? We can, for example, pass synthetic instances of job applicants through a classifier, right? We can create millions of synthetic job applicants, run it through the classifier, and see how things change, right? We can flip one attribute of somebody who's real, creating an artificial person who's only changed that one attribute, and ask what changes. Again, you can try this with people. You can sit down with with a hiring committee with a CV and say, suppose this person had graduated from school X and not school Y, would you have made the same decision? And they'll say yes or no. But the problem is we can't know what they would have done in that situation. And that's sort of in some sense a huge difference, right? We can actually know what the algorithm would have done in that different situation. So these are sort of the opportunities that we have. And because the problem of attribution and the problem of detection is so central to the study of discrimination, right? That so much of the challenge of discrimination is in the determination of where did the discrimination take place, that the opportunity to do these kinds of probes is, in a sense, a big opportunity. Now, I should say, of course, well-regulated here means includes a lot of record-keeping requirements, right? The idea that, a firm, or an online platform that's making these decisions should have to keep some representation over time in some, even if it's an online algorithm, of the training data it was using, the objective function, the training procedure. That's a lot. And obviously the argument can be made that's not technically reasonable to demand. But we should notice that actually in other fields, in other sectors of society, the government does impose enormous record-keeping requirements, right, when they believe it's important enough. Take financial markets, for example, where, again, to sort of make this argument briefly, where trillions of dollars are transacted, society has decided that the danger of misbehavior or the danger of sort of, recklessness is sufficiently high that we're going to require an enormous amount of record keeping about transactions, even though there's an enormous volume of transactions. Now, that's an enormous burden on firms in that space who would much rather be using those resources for something other than record keeping, yet we make them do it. And so in some sense, that's sort of, the point, that this is a question where society has to decide, is the priority high enough here that we want to impose that burden. But having sort of set this framework, let me talk about some of the things that we might be able to do if we can actually analyze the machine learning pipeline. And I'll start with just at a very high level, sort of an extremely abstract point, using some notation, to sort of argue that in principle, this enables us to decompose sources of bias in algorithms. And then I'll do something more specific where we start to think about some of the more subtle ways in which the process of the machine learning pipeline can actually allow us to discover things about where bias may be coming in. So first, the high level point about how we might characterize disparities from a machine learning pipeline. So again, my model of a decision problem, let me make it slightly more specific. I have individuals being evaluated, again, say for a job or for admissions. Each one has a feature vector x. I have a productivity function f of x as a function of these features. I'm sort of imagining that neither of these is truly knowable, right? So the feature vector x, everything relevant to my decision, everything relevant to how good they would be as an employee, is some enormous feature vector containing things that I could never realistically measure. But let's imagine that in some sense it exists. Similarly, there's some actual productivity they will have as a function of these relevant variables. Again, that's in a sense unknowable, but it's useful as a benchmark to have it out there as something that exists. Now, I'm concerned about disparate impact. And so let's imagine there are two groups and I'm measuring the disparate impact between these two groups, an advantage group A and a disadvantage group D. Now, if I know the feature vector x, which doesn't include group membership, I know everything I need that's relevant for productivity. So in that sense, I'm imagining decision makers who have no incentive to engage in bias, because if you tell them x and they're trying to maximize f, that's all they need to know. Nevertheless, there could be disadvantage because the feature vectors themselves are distributed differently across the two groups, right? If you're in the disadvantage group, it may be more costly for you to acquire features, through education, through training, through access to opportunities that produce high productivities. So, right, I can compute the average value of f in each group, right? So in both cases, it's a sum over x, a weighted average of the f of x values, but it's with different weights, the relative frequencies of x in group A, the relative frequencies of x in group D. And as a result, there's this difference in means, right? The weighted average in A minus the weighted average in D. And following the terminology in the social sciences, I'll call this the structural disadvantage between the two groups, right? This is saying we're at the threshold of making a decision about job applicants. But before we ever got to this moment, upstream of anything that we did, there's already disadvantage in society expressed as this difference in means. And so the question now becomes, if we say deploy an algorithm to make these decisions, we could ask, as a result of the algorithm, downstream of the algorithm, has the disparity gotten larger? Has it gotten smaller? And all of these are important questions. We could, for example, say our goal is to not widen the structural disadvantage. We could say more strongly that our goal is to actually reduce the structural disadvantage, that we'd like to deploy algorithms where D of f gets smaller. But it's useful to appreciate that that's the question that we're asking, right? That there is this disparity that's upstream of anything that we're doing. Now, because it's in the nature of the machine learning pipeline to morph this function f into some kind of abstracted version into a trained version, it's going to be useful to have this d notation for any function, right? So for any function v of feature vectors, we could say d of v is the difference in averages. And so with that in hand, let's actually talk about how the machine learning pipeline starts to morph the functions that we're working with. So you could argue that a kind of abstract view of this pipeline is to say, what happens? First, the algorithm designer who wants to deploy a machine learning algorithm for making hiring decisions, F, as I said, is unknowable. So they think hard, they work with their colleagues, they kind of try to imagine everything that's relevant to the sort of job success, and they write down some function G that's designed to approximate F. Similarly, X is really kind of unknowable. And so they're not really working with X, they're working with some reduced representation R of X. Now, there's a sort of syntactic compatibility thing going on here, which is G was designed to operate on long feature vectors X. Now they have a short feature vector R, so they have to use a correspondingly abbreviated function H. Right, so they're really not working with G of X, they're working with H composed with R of X. So first apply R, then apply H. And finally, all of this is them building a model. They then have to actually train the thing. And so, training involves taking a finite amount of historical data and producing not H, which is sort of the ideal function, but some trained function T. And so at the other end of the pipeline, I don't have F. I have T composed with R, right? I have our reduced representation and a trained version of my own particular model of the function. And so the question really is, what is D of T composed with R relative to D of F? And in some sense, the answer is it could be larger, it could be smaller. And our point is actually, in this particular argument, not whether it went up or down, either of these is possible, but the fact that I can write D of T composed with R in a particularly expansive form that lets me see where the different sources of bias have come in, right? So let's imagine the following extremely extensive right-hand side of this, which basically just says this is a telescoping sum that cancels out to D of T composed with R. But notice that how it now decomposes D of T composed with R into the 4 different components that we've been talking about, right? D of F, the structural disadvantage that preceded our decision. D of G minus D of F, which is our bias from the choice of outcome measure or objective function. D of H composed with R minus D of G, that's the bias from the way we've chosen to represent applicants is feature vectors. And finally, D of T composed with R minus D of H composed with R, the bias from our training procedure. Right? And so simply by deciding to sort of carefully model the machine learning pipeline, and if we had access to the objective function, the features, and so forth, we could mechanically write down a decomposition into different things. Again, something that we really, right, even this is not something that we could realistically do with humans. It is something that we could do with algorithms. Okay, so that's at an extremely abstract level, the argument that there's an opportunity for this kind of computational analysis to identify mechanisms that lead to bias, right? That there's a fundamental attribution problem, and algorithms make the attribution problem, in a sense, more feasible. Let me now kind of go one level deeper into this nature of simplification, right? That the crux of this whole pipeline is to take this very long feature vector X and to reduce it down to something that I find manageable, right? And in doing so, we can then try to interpret the function, this simplified function, and look at what's taking place with it. Okay, so let me talk about that. And again, just to recap the model, applicants described by Boolean variables, a productivity function. Let me actually move from the machine learning prediction also to a decision itself, right? So after I've done all this, let's imagine that what I'm going to do, and let's say let's change the story to some kind of something where maybe I'm running graduate admissions. And so I get an F value for each applicant. I'm going to sort by F value, and I'm going to admit the top R fraction, right? So that's how I'm turning that into a decision. We have groups A and D as before. The function is independent of the group. So again, we imagine a decision maker who's trying to maximize F so that they can sort and rank. But this decision maker, even though they want to maximize F, has no incentive to engage in bias, right? They're not particularly trying to address the structural disadvantage, which we might want them to be doing. On the other hand, they aren't biased one way or the other by these groups. They're simply using this feature vector X. And for the disadvantage, I wanted to model it for this part of the discussion in the following likelihood ratio form, to say that my disadvantage condition is going to be expressed as if X is a better feature vector than X prime for applicants, it produces a higher value of productivity, then the relative abundance of X in the population in group A relative to group D is greater than the relative abundance for X prime. Okay, so better feature vectors are more overrepresented in group A. Okay, so having taken all of this notation, what I want to do is walk through an example of how a decision maker would use all of this in the context where they're simplifying down the representation. Talk about sort of some things that go wrong in this situation, some ways in which bias can actually creep into the process. Also some opportunities for interventions. And then what I'll do is I'll state a theorem that says that what happens in the example is actually happening in general. Okay. So I wanted an example that we can all kind of process in our heads in real time. So here's an extremely simple function. But actually, many of the things I want to talk about show up in a function even this simple. So the decision maker is trying to rank people by f, and f is simply a conjunction of two Boolean variables, x1, x2. Right? If you want to keep the running example of graduate admissions in mind, maybe x1 is, grades. Did you have high grades or low grades? X2 is research. Did you, as an undergrad, do high quality undergrad research, or did you not? Right? Well, 1 or 0. And my true criterion is the conjunction. Again, extremely stylized example, to say the least. Now, each of group A and D is half the population, and applicants in group A have each xi set independently to 1 with probability 2/3. Okay. So in the independent coin flips. Applicants in group D have xi set equal to 1 independently for each value of I with probability 1/3. That's the nature of the disadvantage condition. So I can summarize everything in this truth table on the right, this 8-line truth table. So what does the decision maker do? They sort, if they had access to f, and granted, it's not particularly hard to compute f in this particular situation, at all small admission rates, all admission rates up to 5/18, which is the fraction of the population that has f equal to 1, all the admitted applicants have f value of 1. And so the decision maker is basically perfectly maximizing f, and a 1/5, right? If they're basically pulling indistinguishably from the pool of people who have f value equal to 1, then 1/5 of those people will be from group D, right? And that's where the disadvantage is manifesting itself, because group D is going to be heavily underrepresented in the population you're admitting. Okay, now let's talk about where simplification comes into play, right? The fact that it's in the nature of the machine learning pipeline to reduce the feature representations that we're using. Obviously, again, for my stylized example, there'd be no reason in this particular example why your brain couldn't process x1, x2. But let's imagine, for the sake of this simple example, that we decide to simplify f by collecting only x1, not both features, right? Why is that? Maybe collecting x2 is too expensive, right? So for example, I'm doing admissions. Grades are cheap to look at. I just look at grades. It's hard to look at someone's paper and decide, is this a good paper or not? Okay, so I'm just going to collect x1. Maybe it's because just, it's a very wide feature vector. It's just too hard to work with the full feature vector. Or maybe even it's for the sake of out-of-sample generalization. Maybe what I'm doing is I'm actually regularizing my decision rule to get better fit on held out data. And so I'm simplifying. And this third bullet point is actually sort of intriguing and something that we're still kind of trying to explore, that it feels like there's some connection here between the act of regularization and the kinds of dangers of bias that we're about to see on the next few slides. Okay, so if I do that, then I've basically collapsed this 8-line truth table down to what I'll call an F approximator, which basically collapses rows of the truth table and leaves some things as wildcards and has an average value of F here. Okay, and this is obviously a structure that we see in almost any application of machine learning has some version of this. Okay, so in this, again, now we sort of pull indistinguishably from the first row, and once we've exhausted the first row, we pull from the second row in our ranking. And that means at all small admission rates, where we're still consuming from the first row, the average F value is now 5/9, not 1. And we can just do the averaging there. But the fraction of group D is now 1/3, not 1/5, because 1/3 of the people in row 1 are from group D. So relative to the true F, we have gains in equity, more people from group D, losses in efficiency. And it's certainly true that trade-off is present here. But there are also two more subtle problems that creep in once we've done even this level of simplification. And so I want to talk about those. The first is a genuine problem. The second is sort of a potential missed opportunity for productive interventions. Okay, so the first is the following, right? I've said throughout, the decision maker here is maximizing f, and it is sort of in our story, the decision maker is kind of, lazy in sort of not caring about the fact that they're, essentially working in a system that has this profound structural disadvantage, right? They're laser-like focused on f. They're not particularly interested in trying to correct structural disadvantage. On the other hand, they're also not biased. They're not looking at the value of group membership when they make these decisions. And so if you would ask the decision maker, with the 8-line truth table, would you like to know the value of group membership? They would say, no, I don't care about group membership. I know everything I need to know from x1, x2. Once I project out x2, you ask that same question. Would you like to know the value of group membership? Now the answer is, in fact, yes. I actually, if I'm maximizing f, would like to know the value of group membership. Because if I knew it, I would convert this 2-line truth table into a 4-line truth table, where people with x1 equal to 1 and group membership equal to a have an average f value of 2/3. But if you have x1 equal to 1 and group membership d, you only have an average f value of 1/3. And so you would actually get a higher, for every admission rate, you would get at least as good and usually strictly better average value of f as you admit from this 4-line truth table. In other words, simplification has transformed disadvantage into bias, right? That where once upon a time the decision maker didn't care about the valid group membership, now they do. And why do they? It's because you projected out information. And what's interesting is that this actually relates quite closely to some of the points from the very beginning of the talk, that the arguments about the formation of negative stereotypes is that negative stereotypes are particularly likely to form. You're in particularly dangerous conditions for negative stereotypes when you're in low information or rapid decision-making environments, right? That's when humans tend to fall back on stereotypes. We see this in other ways in policy domains, right? So for example, there's been recent work over the past 5 years on studying so-called ban-the-box policies, where you have job application forms, and the law says, we're going to prohibit you from asking certain questions on job applications, right? Certain boxes that people used to check are now banned from the job application because we think it's perpetuating disadvantage. A number of people, including this very influential paper of Amanda Agan and Sonia Starr, looked at jurisdictions that had implemented ban-the-box policies and showed through clever series of experiments that in aggregate, employers were engaging in an increased amount of discrimination in places where ban-the-box had been introduced. Effectively, they made the argument that employers were, consciously or unconsciously falling back on stereotypes to try, in a sense, filling in the information that was being withheld from them because they couldn't ask these questions. This is, in a sense, exactly what's happening in our extremely simple example. We withhold information, and we take a situation where the decision maker didn't care about group membership, and we've incentivized them to care, right? And so what's interesting is that we tend to think about this as a very human thing to do in low information settings, to fall back on stereotypes. But in fact, what this is arguing is that an 8-line truth table will do this also if you instruct it to care about f and you withhold information from it. Now, the other point I want to make, which shows up even in this extremely simple example, is that simplification isn't even an optimal trade-off between efficiency and equity. It's not even on the Pareto frontier of efficiency and equity. Because here's another thing that I could do with this truth table. I could try to strategically unsimplify it, right? So I start with this approximator. And what I could do is say, suppose I want to increase efficiency and equity simultaneously in my admission rule. I could go into the first row and I could sculpt out a subcell and put it at the very top of the truth table. I could say, if x1 and x2 are both 1, and group membership is D, I'll admit those people first. Then I'll move down through the truth table in order, right? First admit from the first row, then the second, and apply the first row that holds for the applicant, right? And so the point is, what's happened in this unsimplified truth table? Efficiency went up because for every admission rate, the average F value is now at least as good, and for some admission rates, strictly better. And equity went up because for every admission rate, the fraction that's coming from group D is better than it was in the simplified rule, right? So if I think about all possible approximations to F and I organize them on this sort of 2-dimensional scatter plot of what's the efficiency and what's the equity as a function of the admission rate, then the simplified rule is not on the Pareto frontier because I've improved it in both things. Right? It was never the best choice. Now, here too, you could ask, this is sort of a mathematical operation that I'm doing, sculpting out a cell. But for anyone who's been involved in graduate admissions, you sort of recognize the activity. it's the activity where the admissions committee says, or the department says, we don't, we feel like we're not getting enough people from group D in our entering classes. What if we were to create an internship program? In the summer, people from group D come work with us over the summer as undergrads after their junior year. They do research with one of our faculty. And the people who do really good research, we sort of keep track of that in our admissions process. What have you done? You've said, it's very expensive to learn about people's research. But what I can do is sculpt out a particular subset, namely people from group D who did do research with us and did great research. And the argument that gets made qualitatively is exactly the one that's being made on this slide, which is I've now simply improved my admissions process because I'm going to have this set of people who I know are great and come from group D. And so I've increased efficiency and equity simultaneously by investing slightly more resources. And so there actually is an interesting resource expenditure question here, right? If I have a simplified rule, and it's been simplified out of necessity, I literally can't collect all the features I need to collect. How would I sort of strategically unsimplify it in a controlled way to actually simultaneously increase efficiency and equity by as much as possible? Right? So that's the picture that you could have in mind. I started with f. F is some complicated real valued Boolean function. And there's a kind of landscape of all possible simplifications of f. And when I simply project out variables, as I did here, I'm at this interesting sort of fork in the road on the landscape, where in one direction I can tilt into incentivized bias, getting decision makers to seek out the value of the protected attribute in ways that work to the detriment of the disadvantaged group. And in other directions, I can move toward Pareto-Improvement, simultaneously improving in efficiency and equity. And so the theorem that we were able to show coming out of this work is that what holds in this example holds in general. So for every real valued Boolean function f that satisfies this disadvantage condition that I stated, and also a genericity assumption, which I haven't stated, effectively the values of f are in some kind of a general position. And for every simplification of it, which can be a little more general than projecting out variables, but basically means partitioning all the feature vectors into cells where each cell is defined by fixing the values of some variables, then two things hold. One, that there's always a Pareto improvement. There's always an F approximator that strictly improves on G in both efficiency and equity. And two, this incentivized bias problem. If G does not use group membership, then adding group membership as a variable increases efficiency and reduces the equity. In other words, it creates a pernicious incentive to engage in bias. It's an incentive because a decision maker who doesn't care about group membership but just wants to maximize F will suddenly become actually incentivized to seek out group membership. And it's pernicious in the sense that they seek it out in a way that harms group D. I want to talk about just one point sort of in how we prove this theorem. Because there's in some sense this example obviously makes things extremely simple. There is one sort of tricky point here, which is what I'll sort of focus on for 2 minutes. Which, in order to see where the trickiness comes up, it's useful, as it always with things, to sort of weaken one of the assumptions and see that the theorem stops holding. Okay, so let's imagine that we took our disadvantage condition, which was this relatively strong likelihood ratio condition that good feature vectors are more overrepresented in group A. And let's weaken it to a simpler disadvantage condition that simply says the means of F are different between the two groups, right? So let's not have a vector by vector comparison. Let's simply say the weighted average of F in group A is higher than the weighted average in group D. In that case, the theorem as stated here would not hold anymore. We can get weakenings of this theorem, but it's instructive to see why it no longer holds. And that's where we get to this example that I have here. This is a more complicated example, not one that you can really work out in your head in real time during a talk. But let me tell you the property it has. The property it has is that if I were to project out x2 like I did before, the decision maker would again have an incentive to seek out group membership, but actually in a way such that they could favor group D. Okay, so group D has a lower mean value of F. Yet when x1 is equal to 1, group D has a higher mean conditional on that. And when x1 equals 0, they also have a higher mean conditional on that, right? Which is, of course, weird, right? D has a lower mean, yet whatever I tell you about x1 means that D now has a higher conditional mean. And that, of course, is Simpson's paradox from statistics, right? The fact that this can happen is surprising but true. And it's actually sort of central to everything I'm talking about here, because when you have Simpson's paradox, it says that actually D has a global disadvantage effect, but conditional on certain pieces of information, that relationship might flip. And essentially what we're showing, the crux of this, is that the disadvantage condition that we have, which is vector by vector, right, this likelihood ratio condition, actually smooths things out sufficiently that Simpson's paradox can't happen, right? So the crux of what we're doing is trying to use this condition to prove what you might call an anti-Simpson result, that you can't get Simpson's paradox when you have this condition. And so the basic sort of combinatorial point that we need to make is, if we have this condition on F, and we consider any non-trivial partition of the feature vectors for A into cells, and partition of the feature vectors in group D into cells, and we assign averages within cells as our approximation, then there always exists at least one feature vector X for which our estimated value in group A for feature vector X is strictly higher than our estimated value for group D for feature vector X, right? That's what doesn't happen in this example, but which always happens when we have the likelihood ratio condition. And this one feature vector X sort of becomes the handhold that we can use to get the Pareto improvement and to argue about incentivized bias. Okay, so that's effectively that's not a sort of picture of sort of what the proof is doing, but it's a picture of sort of what the proof has to do in order to get this to work. It has to show that what happens in this example, something like Simpson's paradox, can't happen in general. So with that, I want to wrap up. This has been sort of a sequence of points about what happens when we apply the machine learning pipeline in decision making, and the sort of fundamental operation of simplification, which we might do for reasons of cognitive complexity if we're humans working with the algorithm, and we might do actually for reasons purely internal to the algorithm, for reasons like regularization. Okay, and what we see is that a number of subtle effects happen, right? That there's an incentive, right? It creates an incentive to seek out group membership in ways that might not have existed before you simplified, and that you have the opportunity for these Pareto improvements. There are a lot of other questions that we could ask, right? We could consider, for example, other formulations of simplicity, right? All of the ones I've been talking about are sort of aligned with, projection or shallow decision trees, things that choose to ignore variables. We could also think about syntactic simplifications, right? What if I'm constrained to use a linear approximation to F, so I can read all the variables, but I want to use a syntactically simple form? The questions there get interesting and complicated in ways that we don't fully understand yet. And of course, just this whole idea of studying the space of all possible simplifications. But I think, backing up the sequence of arguments that led us to this point, the broader point that I think Jens, Sendhil, Cass, and I arrived at in thinking about these questions was simply that algorithms in these domains, in decision-making domains, allow a new level, really a dramatically new level of concrete, explicit discussion about the decisions we make, where we're actually forced to explicitly list, write out our objective functions, list the features that we're using, and to think about how different that is in a context like auditing for bias or evaluating claims of discrimination, right? That there really is not just a quantitatively different conversation to be had as we use these large amounts of data, but a qualitatively different conversation as we change the way we engage in decision making to work with explicit objective functions and explicit features. And obviously the point, which I think, is very much behind the kinds of activities that you're engaged in here with this kind of interdisciplinary work, is that many fields are going to need to play a role in setting these priorities. And I think it's certainly, as a computer scientist, I think an opportunity for, for me and people with the kind of background, like me, that to think about how we might be able to sort of play our part in these kinds of conversations going forward. Thanks very much.
Great, thanks so much, Jon. That was a really interesting talk. I found a lot of really cool insights in this work. If anyone has a question, feel free to unmute yourself and ask. But actually, if you don't mind letting me kick it off, I really liked how you decomposed the sequence. It's kind of a very simple but very nice observation that you can, once framed this way, you can kind of think about all the different parts of the pipeline in which bias creeps in. And I was wondering if you had any thoughts as to basically which of those entry points are most conducive for intervening.
Yeah, that's a great question. I think we're going to sort of learn as we go. I think we're sort of at a new point in the situation. I think, so just a few observations. Like, the choice of objective function is something that's maybe the most under human control in a way. Like, I think, the choice of features is partly a decision that we make and partly constrained by just the resources involved in collecting features of certain kinds or imputing features of certain kinds. Similarly, the training procedure is, partly under our control, but partly it sort of operates under things that are sort of a little bit beyond our technical ability to fully understand. The choice of objective function is often something that's made up in a relatively ad hoc way by people who don't necessarily always appreciate the gravity of the choice they've just made. And so I think we see, like even just distinctions like if I'm training a rule for admissions, I could do one of two things. I could say, I would like the objective function to be based on how well students did in our program once we admitted them. Or I could have it be based on what decisions do we make for people like this in the past. The second one is very clearly saying, I would like a rule that simply perpetuates whatever I was doing, biases and all. The second one is sort of, a different kind of measure that says, we have the ability, to look into the future with our past applicants and see how they actually turned out. And so even that choice, and that's of course a choice that I think people are aware is a big distinction. And, you see companies talking about, we took people and looked how they were scored on our interviews and then looked at how they did at the company. And we discovered that like interviews were not a great predictor. And so I think that's a sort of realization that people have had. But one interesting point is how you can sort of derive that realization by sort of appreciating that that's simply look at the objective function that you chose and ask like, what were the, list for me 5 possible objective functions and then evaluate the pros and cons of them would already get people, I think, to a point beyond where they often are with these things.
Yeah, that makes a lot of sense. Thanks. And then, I'll wait a moment in case anyone wants to jump in.
This is Dana Anglin.
Hi.
Thanks for a very nice talk. I'm a little troubled by the seductiveness of the analogy between machine learning prediction and this kind of decision making. One of the aspects that gets simplified out of the model. So imagine that I'm a woman applying to a computer science program, graduate program. And I look really good in my sort of individualistic productivity function. And I'm admitted, and lo and behold, I'm the only woman in the class. And my productivity function does not actually predict my productivity because of the conditions that I find in the group of people that has been admitted. So the individualistic assignment of a feature vector to an individual as being fully capable of predicting their future performance in the situation in which the decisions have been made about, say, other people, seems to lose a significant aspect of the process.
Yeah, a fantastic question, of course. And actually, a large part of the paper with Jens, Sendhil, and Cass is actually wrestling with the scenario of what we call, say, like the toxic workplace environment, for example, where people come into an environment and now actually their success, in part depends on the environment they find themselves in. And so that now creates a slippage. I mean, in some sense, almost by definition, that slippage is going to show up somewhere in the, if we're fully decomposing the disparity, it's that slippage will show up somewhere. But the point is to appreciate that is one of the things that has to be sort of interpreted in the model. And I think, one thing that we've begun doing.
The point, roughly speaking, is that my productivity may not be a function entirely
just
of my
view,
attributes.
but of the set. Yep, absolutely. And so one thing that we've been looking at recently actually is drawing on the work of Scott Page, University of Michigan, who sort of has, I think, been the most, one of the most effective people at sort of articulating this point that when I'm hiring a team of people, I should evaluate the team as a set function, not as a bunch of individuals, for precisely this reason. And so I think one thing we've been looking at is actually, there's of course the danger with using any formalism at all for these things, but I think we always aspire to say, okay, if we identify a slippage like you're talking about, can we at least extend the formalism to be able to sort of talk about that sensibly? And so thinking about these selection problems as actually operating on set functions rather than just functions of some individual feature vector X, right? So I'm given a pool of applicants. I'd like to select a subset S. And now the productivity is actually f of S for the subset S, you know, or f of x1 to xk if there are k people in the set, rather than just the individual. And that actually, there are interesting things that you can find there. So for example, with my student Maithra Raghu, one thing that we proved there is in fact that the sort of point you're making, there's an actual negative result you can prove, that there is no function of the individual variables that gives you any approximation to the actual best team you could assemble, right? You imagine I'm trying to maximize, you know, certain kinds of set functions, even ones that we know how to approximate tractably, say, you know, they have some nice submodular property. Nonetheless, of course, what we might do is say, I'm going to give each person an individual score and then select the k highest scoring people. And provably, there is no score that you can assign to individuals that's going to allow you to reconstruct anything approximating the best set function. So I think it's an extremely important point, and one that's motivating a number of the questions that we're asking right now. Yeah, I think it's one of the main things that makes these hard questions.
Thanks a lot.
Yeah, thanks, John. And just one more question that came in over chat. So the question was about time. So do you think there's a time dimension that's important in mitigating bias, and how can that be incorporated perhaps into some such formula?
Yeah, also a very nice question. That, you know, one thing that we're actually, so there's been a number of recent papers, and actually there's a recent work that Hoda Haidari and I have been doing, which sort of tries to add to this literature, on, you know, the ways in which some of these policies that we might be implementing, say, for example, with socioeconomic mobility, one reason why we might be thinking about fairness considerations is for the current generation, to say like we need to equalize things here. Another is for the long-term effect over future generations, right? So if I increase access to opportunity now, then if I sort of imagine that generates opportunities for economic mobility, then, you know, in future generations, I'm going to have potentially reduced the amount of inequality, such that when I go to make that decision process, you know, the same decision process in the next time period, I'm looking at a pool where there's less disparity in access to opportunity. And so what's interesting is you can actually build models of this, and some of these models actually reach back to work by people like Glenn Lowry in the 1980s about the policies that we're making. You can actually put into this very long range thing with discounted reward, and you can almost make a direct analogy to reinforcement learning or Markov decision processes, where I'm literally, in a way that where the mathematical analogy actually sort of stands out, I'm trying to sort of steer society over multiple generations toward a desired outcome with reduced inequality. And there's now kind of a turning radius for that steering, right? Policies could be evaluated on whether I'm trying to do more in each generation or less in each generation. And the sort of trade-off is one that we see in Markov decision processes, which is that, you know, if I steer gradually, then I'm giving up a lot of sort of discounted reward in the future. On the other hand, I'm potentially doing something that's myopically better for sort of F maximizing decision makers in the present. So I think these are exactly the kinds of questions that become sensible to ask. You know, and again, I should stress that, you know, I'm speaking in the language of models because I think there's always an interesting engagement with the sort of more qualitative aspects or interpretive aspects of this problem, where, you know, we talk about models, we ask what the models are missing, we sort of try to use the models to shed light on some of the qualitative questions we should ask. But, you know, that conversation has to really happen in the tension between the modeling activity and the interpretive activity. And I think both are somehow contributing to the conversation.
Great. Thanks so much, John, again for joining us. It was a really interesting talk, and thanks for everyone who logged in and participated.